Hello. So I was presented with some requests about extending this notion of planar graphs. And to that extent, what I will do is to explore a classical question, which is the following. Can we connect on the ground gas, electricity, and water to 3 homes without the cables or pipes overlapping? Well, the idea is that we can model this situation using the following graph. How so? Well, I'm going to label the houses as 1, 2, and 3, and the utilities as G for gas, E for electricity, and W for water. The intention is that whenever we place an edge between in this graph, we're going to connect, for example, home number 1 to gas, to electricity, and to water. We'll connect home number 2 to the same, and similarly for home number 3. And now you may recognize this graph as being isomorphic to a complete bipartite graph 3, 3. So the question is now the following. Is this graph planar? If it is so, then we will be able to answer this question affirmatively. Well, let's give it a shot. So for this time, what we're going to do is suppose that is actually the case. So suppose it is. Well, what can we get from here? Well, then, from Euler's formula, we have that the number of vertices minus the number of edges plus the number of faces is equal to 2, as this is a connected graph. Well, but what do we have in this case? Note that the number of vertices here is 6. The number of edges is 3 times 3, which is 9. And, well, we are not so sure about the number of faces, but let's see if we can impose some conditions. One of the things to notice is that this graph has no cycles of odd order. And you may say, why? Well, the chromatic number of this graph is equal to 2. If it had a cycle of odd order, it would require 3 colors to be colored, contradicting the fact that the graph has a chromatic number of 2. So the smallest phase that we can provide in this graph is that of a cycle of order 4, or of length 4. So the question now is the following. How many cycles of length 4 are there? Well, we don't know, but for example, we have this. The cycle 1, E, 2, G. But then this one indicates the following. Look, if I was to select 2 different utilities, I can provide another cycle like this one, G with W, that produces a new and different cycle. If I was to select another pair of homes, I would produce something along these lines. 1, 3, G, W. So that indicates that at least we have the following. For each unordered pair from the set of homes, and each unordered pair from the set of utilities, we can construct a cycle of order 4, so a copy of C4. But how many are there? Well, how many unordered pairs can we select from here? Well, there are 3 of them. How many unordered pairs can we select from here? Well, there are 3 of them. So we have at least 3 times 3, which is 9 cycles of order 4. Each of them producing a face for this graph. So now we have this. 2, which is V minus E plus F, is at least 6 minus 9 plus 9, which is equal to 6. Well, that's a contradiction. So we backtrack in our assumptions, and the only time that we make an assumption that we cannot support is when we suppose that the graph is planar. So the only logical conclusion is that the graph is not planar. So in fact, we cannot connect electricity, gas, and water to 3 homes without the cables or the pipes overlapping. Okay, I hope that you enjoy it. Take care.